So we're going to be trying something kind of new today. So basically, there's this gorgeous question on screen, and when I saw it, I thought, wow, this could also make for a really great lesson and a really great activity to do with students, because as a math teacher, whenever I see problems like this, I always think, oh, can I make this into something bigger? Can I make it into a worksheet? How do I get kids to access questions like this? So I also made another video, like a short about this, which I'll link here as well. But we're going to talk about, how do we, or how might I as a teacher make this into a worksheet? I'm literally just going to do the process, talk about what I'm doing, and see how it goes. So the first thing I'm going to do is actually, because I'm going to share my whole screen, first thing I'm going to do is get the question again. So we're just doing the whole process here, like not much editing, talking through how I would actually do this. So to start with, let's look at how we would actually answer this question. Because we want to find the square root of a number, and finding square roots is notoriously quite difficult. But what's cool is you can actually do a nice trick for this. You should pause the video and try it yourself, by the way, before I do it. But I'm going to go through it now. You might have seen this video already. So what I'm going to do is that you just break everything into its product of its into a product of its prime factors. So you can do that using trees, for example. So you might write 54 as 2 lots of 27, which is 3 lots of 9, which is 3 lots of 3. So you might want to do it like this. And actually, the way I'm imagining this lesson working is we would have already done product of prime factors, and this is like an extra bonus thing of what can we do with it. So you might write this as 2 times 2 times 3 times 3 times 3. You might have also talked about index form. So 54 is also 2 times 3 cubed. And eventually that is going to make all this a lot neater. Similarly, 147 is 3 times 49, which is 3 times 7 times 7. Like that, because it's 3 times 49. And you also could have done that by doing a proper product of prime factors, doing its factory. And eventually, when you go through this, when I go through this in a class, that is how I would have done it. So now I've broken it down into its prime factors. What I can do is I can start grouping them together. So what I have is 2 squared times 3 to the power of 4. So this is already a nice way of practicing getting things into index form, times 7 squared. And you might now see how we could solve this, because what this is really is 2 squared times 3 squared all squared times 7 squared. And actually, we can rewrite that as 2 times 3 squared times 7 all squared. And then the squares and the square roots cancel out. So this is just 2 times 3 squared times 7, which is 2 times 9 times 7, which is 6. I was going to do the 9 times 7 first. 63 times 2, 126. So that would have been crazy hard to do if you just do the multiplication and square root it. You'd have to do a lot of estimation basically to do it. But this is a great way of doing that. So what I always think about is how could we possibly get students to answer this question? How could we have primed them first to do this? So we're going to build a variation theory-esque worksheet that slowly builds up to a question like this. So we're just going to see what happens. They probably won't, because I'm imagining you can do this really with anyone as a nice problem-solving question that practices 1, product of prime factors, and 2, understanding what square rooting is. And you'll see ways we can extend this later. There's some great extensions we can do with this later. But yeah, you don't need to explicitly teach rules with surds, like this step to this step. You can just do lots of simpler examples and extend it to this. So that's what we're going to talk about. That's how we're going to do it. So let's keep those, though actually we probably don't need them anymore. Okay, so let's think. Recap. Let's look at just square rooting. Square rooting examples. So I'm literally planning this lesson as I go along using equation editor, obviously, because it's Unreal. So what I'm thinking is doing a bunch of really simple ones, and you could do this as a matching activity, for example. Like square root of 9, and then also what's nice, I think, always is doing things like this. So the square root of, oh no, that's the wrong backspace. square root of 3 times, oh, no, 3 times 3, like this. Similarly, so what this could be is lots of quick fire questions that students hopefully do. In fact, I'm just going to start copying and pasting, so that's going to make my life way easier. That hopefully you can talk about how that they're the same, the patterns between these are exactly the same. So for example, these three, and you could present it as like match up the things that are equivalent, which actually might be a nicer way of organizing this. I think that probably is what I'll do for this. You can talk about how these three things, and what I would talk about is these three things are all the same. The square root of 9 is exactly the same as the square root of 3 times 3, because we've just broken up this 9 into 2 pieces, which is the same as square root of 3 squared, which is the same as 3, because we're recapping the idea that 3, or square rooting and squaring, are inverse operations. So we've got those things. Let's actually... I'm just going to do some more examples of these. So, in fact, let's just paste this in. So let's do another one that's very, very similar. Square root of 16, which is 4 times 4, which is 4 squared, which is 4. And actually, what's nice about this one is why do we include another couple of things that are equivalent to this? So, for example, the square root of 2. Now, I'm going to times actually. I'm going to click it. 2 times 2 times 2. Oh, that's actually this whole thing. That does not work. Let's grab. Let's again. Let's here. And then 2 times 2 times 2 times 2. That's the same thing. That's the same thing as, for example, 2 squared times 2 squared. 2. And what I want to do is just getting my students to talk out why all these things equal. Why might you want to do one of the things and not the other? For example, why might you want to put it in a form of 2 squared all squared? Why might you not? Like this, like a needless step. You can see this something similar. Is it going to be 2 squared? No, that seems strange. Huh, why don't I do 2 squared all squared? Let's try and sort that. 2 squared in brackets squared, and then all of this in brackets. And then let's see if we can. Equation editor, why are you being like this? Cannot do square root 2 squared. Squared. Oh, yeah, no, I can. Okay, wait. I might take that out. I don't think so finicky. Okay, that's a very long time. So I think what I'll do here, I think this will be match up each equivalent square root. I think we separate these out. Let's do one harder one. So for example, let's do the square root of, why don't we do 12. I'm thinking of a way of using 3s and 4s. And actually this would be better if it was loads of different text boxes. No, we're going to just say, can you explain why? Yeah. We don't need this, we don't need this. So, and actually we'll probably do it in a way where it reveals itself slowly so it's not too overwhelming. And then let's get one more. And here, let's do 3 times, no, wrong backspin, 3 times 12. Yeah, let's do this, 3 times 12. Because, and then let's do another one, which is 3 times 12 times 4. Now, the reason we're doing this is this one, what you can do is you can obviously just multiply them together. You can do 3 times 12 and see what it gives you, and it gives you 36, and then you can just square root that, which gives you 6. Or you can talk about the fact that you can break it up like you've done with these 2 bits on the left, because this is also 3 times 4 times 3, which is 3 squared times 2 squared, which is also the square root of 3 times 2 in brackets squared, like that, which is of course 6 as well. All of them are 6. And this one is to talk about the fact that once you've done all these multiple, if you can break it down like this one here, you probably don't want to, or here you might multiply it and do the square roots, but here you just start getting too big numbers to really want to do that. So is there a nicer way you can break it down? And then this one would probably just actually show the working out for. This one will show the working out for. So we'll probably do this in a way where this starts, so this appears, then, oh, is this not in the same one? No, it is. Then this one does, then this one does, then this one does. So how this might work is, maybe as a starter even, we have these on the board, these ones on the board, and we talk about the fact that they're pretty much all, each column is exactly the same. We can get kids to talk about why that is, how they did it. Specifically talking about maybe these 2 examples and this one and why it might be easier to do that. Then we can look at a slightly weirder one and talk about how you can multiply out or not and how that can give you a nice answer. And then we can talk about this one, which is one step harder than this one on the left, and we can do that. Now what we might want to do next is, oh, not that, is give kids 2 questions, a classic example, and then your turn thing. Okay, I'm not sure why it's not letting me copy and paste that, but whatever. So let's do, let's grab this. So we've done some talking about square rooting. Once again, I'm envisaging this being after you've done breaking down into prime factors. So kids should already, probably don't need to do an example of that already. And actually you'll be doing examples of stuff similar. So let's do 9 times 16 times 4. They're all square numbers, so that does make it easier. And then we can similarly do 9 times 25 times 4. So they're 2 simple ones. So how it works is, teacher goes through this one. I could just copy and paste this straight from variation 2, but whatever. So this would be example. And then this would be your turn. And you can see they're very, very similar. They're very similar. So the kids will see us do the one on the left, and then we'll do the one on the right. So, for example, how I might talk about this is breaking this down into its prime factors. So this is 3 squared. And actually what's nice is with 16, you can talk about the fact that you don't need to, you really just need to break it down into squares. So that's times 4 squared times 2 squared. So talking about building blocks of numbers, then that is exactly the same as 3 times 4 times 2 all squared, because you are squaring each bit, so it's basically the same as it all being squared, which is just, because the square and the squares cancel out, 3 times 4 times 2, which is 12 times 2, which is 24. And also we can talk about the fact that if you do 9 times 4 times 16, so 36 times 16, which is 6 times 3 is 18, 21, 0, 6, 3, 6, 7, 5, 576. Finding the square root of 576 off the bat, that's pretty hard. You're going to need to use some sort of trial and error. And you can see that this question, when we look at this one, for example, doing the multiplication is just a lot longer. So this is a nice way of showing kids shortcuts to nice questions. And actually, if we were finding the square root of 576 just straight off the bat, which might be a nice example to do as well, you can split it into its prime factors and then do it. And maybe that would be a cool example to do as well. I think there's pieces missing here, but that's fine. And then they do this one. And actually, yeah, And then they would do that one. So what is missing here is an explanation of this step, I think. This step. So I think it's just important that we fill that in. So we talk about this step. Just so we're saying, why does this work? Why does this work? Okay, so we know we can do that step. I think what's missing maybe is a question like where you're really getting them to practice the skill. So let's get a square number. I'm just going to do this on a calculator on my phone. And let's do, for example, 45 times 45. Oh, that's going to be ugly, but it's fine. Let's say you had to do this question. How on earth would you do it? How on earth would you do it? And what we might suggest is that this is a great way to practice our product of prime factors, because this clearly divides by 5. And so we need to do, how many times does 5 go into 2, 0, 2, 5, 0, 4, 0, 5, 405. So we've got a 5 clearly. This also divides by 5, 5 into 405. 0, 81, 81. This is 9 times 9. And what's nice actually is you can talk about the fact that for this example we can stop here because we've got pairs of numbers, we've got squares, but we can keep going. 3, 3, 3, and 3. And so we have that 2025 is 5 squared times 3 to the 4, which means that it's 5 squared times 3 squared squared, which means that it's 5 times 3 squared all squared, which means that the square root of 2025 is the same as the square root of that, which means it's just 5 times 3 squared, which is 45, which is so nice. Like, I really think if you get kids, although 2025 maybe you could do, because 40 times 40 gives you 2000, I think. No, it doesn't. Yeah, this is hard. It's really hard to do the square root. Maybe that's also a nice question to have as part of the starter that we come back to later. I think that is a good idea. Like, how on earth would kids do this? Like, how on earth would kids do this? This is a nice question to have at the beginning. So we can talk about how would they do it, why is it hard, and then we use our trick to show them how they could have maybe done it easier. So we'll tidy that up. Let's see how long we've been recording for. 20 minutes, that's pretty fine. Okay, and then we talk about how we do this, and then we get kids to do something similar. Probably on a new page, actually. We might have done this on a whiteboard. Let's get another weird square. Let's do, I don't know, 32 times 32. 1,000. Oh no, God, there's so many 2's there. 34 times 34? Trying to find any square. How about, let's do 35 times 35. 1, 2, like this. Okay, that's pretty similar. Okay, cool. So then they do that one, that's nice. And now let's do some variation shenanigans. So worksheet. So then students, and what I'm going to do is I'm going to do loads of questions, like absolutely loads of questions that will hopefully kids can work through. There's this idea of reflect, expect, check, explain, which I've talked about in blog posts, but you can also look up Craig Barton or Legend. But it's also about lots of questions where there's a little bit of variation each time, and kids need to use their previous answers to help with their next answers and compare, think what's changed, think what's the same. So I'm not sure about this slide, really. I think this will be part of the starter. I think maybe I'll give this whole thing as part of the starter. Give them like 5-10 minutes to do it. Even still, we want to copy this back. So I think I want to do individual questions. So I don't want this. I probably actually want... Okay. Let's copy this. In fact, at the end I can just unitalicize all of it. So that's exactly the same as 7 times... No, I keep doing the other one. 7 times 7. In fact, let's just throw in a... Let's just throw in a 7 times 7 times 1. Just show that the 1's irrelevant. Then why don't we do... What do? 7 times 7 times 2. 7 times 2 times 7 times 2. This one. And then let's just copy this and do basically exactly this. Nope. Basically exactly the same, except rewrite these because it doesn't matter where these are. And hopefully these should be done pretty quick fire. What's nice is we can discuss at each step, or kids can think about at each step, and we can discuss at each step what's interesting about what they've done here. 49 times 4. Like, hopefully kids are not doing each of these questions individually, they are using previous answers to get their questions. What is 49 times 4? It is 50 times 4 is 200 minus 4, 196. Yes, they're saying, look, you can do 196 by just splitting up kind of backwards. So now we can even do the square root of 196 times 4 again, because actually that's just going to be 2 times 14. That's also nice. Let's do some squaring ones. Let's put another one in here, which is 7 squared times 2 squared. Just to make sure that people see that these are exactly the same. Let's grab the whole thing. Let's keep going. This should be... Oh, actually, no, that is annoying. I should just do columns. Which I should obviously know how to do. Oh yeah, okay. Okay, then we can do, oh no, 196 times 16, that could be the next one. Then we can even do 196 times, well, in fact, we could do 49 times 16, so we can see that actually it's just, that's times by 196 is divided by 4 to get to 49. What's the going to happen to the answer? Which, yeah, that'll be cool. Then, what would be a nice next one? Maybe we'll add another piece in. 49 times 16 times, no, that's the wrong backspace, times that's 25. In fact, let's add some more squaring ones. 7 squared times 4 squared, which is actually exactly the same. Let's copy this. 7 and we might want to do something with yeah, that's fine. Okay, then how about one where we just have it in pieces? So we have 4 times 7 times 4 times 5 times 5 times 7. Because that's actually identical to the one above, but kids will need to have seen that and worked that out. And then we can also, why don't we do something very similar, but instead of the 4s, we do 3s. Because the point is that all that matters is that these are the same. Yep, and then let's do a completely different one. Whoa, not there. 3 times, let's make these 8s, let's make these 2s. Okay, I think that might actually be enough for now. I think we might want to increase the spacing. That's the only other thing. So if I was actually going to put this up, if I put this onto like a worksheet, then I would give a lot of space between these things. And in fact, I'm still going to add some indentation, some line spacing. Whoa. No, let's do 2. Yeah, let's do that. Okay, cool. And then, once we've looked at all these things, then we go back to our guy here. In fact, let's just copy this slide back. Although we have already looked at 2025. Have already looked at how we might solve that. This goes, this comes back. Now we can look at some extensions, and the extensions here are so cool. Extensions, because we have this number here, and now what we can do is, why don't we just do a crazy one? So let's do 2 times 54 times 147. The best ways to make this yourself is just start on the lowest block. Like start with the prime factors and then build up. But why don't we do 2 times, how do we extend this? In fact, let's not do this extension. Let's do a cube root one. Cube root one is going to be similarly very cool. So extensions, extension 1, cube rooting. And teachers can make their own here, but it's very, very, very similar. We want a cube root there. Let's make this a bit bigger. The cube root of 2 cubed times 3 cubed. And this obviously is exactly the same as what we've done. In fact, let's make this a 4 just so things are a bit different. This is kind of exactly the same as what we've done before. And then let's just get a funkier one. So let's go 2 wrong backspace, that one. 2 times 4. Now actually that already gives me a cube, so that's good. 3 times times 9 would also give me a cube. My new keyboard, the different size backs, like the backslashes all the wrong way around. This is actually the same thing as the one above, so that's not that fun. So let's go 2 times 5 times 25 times 4, and then let's do a really funky one where we'll go for 4, so there's 2 2's there, that's 2 to the power of 2, times 49, which is 2 7s. Now if I do a 14, then these match up with each other. We now have, we have 3 factors of 7 and 3 of 2, so that will work. And then I can also do 125 for fun. And in fact, now let's do 25 times, because 25 is 5 squared, so now we need another 5. Let's do 5 times 8. There we go. Now these ones, and similarly, instead of needing pairs of things like we did before, now we need sets of 3. Sets of 3. So if we just quickly talk about how we might solve this one. We'll quickly talk about how we might solve this one. We've got that's the cube root of, this is 2 squared times 7 squared times 2 times 7 times 5 squared times 2 cubed times 5. Now we just make them into cubes. We've got 2 cubed times 7 cubed times 5 cubed times 2 cubed, which is 2 times 7 times 5 times 2, all cubed. And now when we cube root this guy, think how hard this would be to do without this method, which is so cool. It's just 2 times 7 times 5 times 2, which is 10 times 14, which is 140. Now imagine this whole number at the top. Let me just do it on the calculator. It's 4 times 49 times 14 times 25 times 40. Yeah, what we've just done is we found the cube root of 2744000, which is crazy. So actually what might be nice is to write that and just make kids realize how crazy it is what they're doing. So that's 2744000. Like, can anyone work this one out? Nope, but we'll see that when we do this one, these are exactly the same. And actually working this one out was pretty easy, as we can see here, pretty easy. Another extension might be extension 2, making square numbers. Making square or cube numbers. And I think this is also such a nice idea. What will I need to multiply the following number by to make it a square number? Now, let's choose a number. Let's choose 75. Okay, now let's look at how we might do this. We've got 75 is 5 lots. Let's do some quick division. I probably should just be able to know this. 15. Which is 5 times 3. So 75 is 5 times 5 times 3. Well, clearly, this is not a square number, because for square numbers, we need the powers to all be multiples of 2. So what do I need to times this by to make it a square number? Well, I need to make this a 3 squared. So it's just, so we need 5 squared times 3 would make it a square number. So 75 times 3 would make it a square number. And so that square number, 3 lots of 75 is 225. And then you could square root that and find that it's just 15. So that's another really, really nice type of question to make it a square number. And kids, and then students can now choose any number between 1 and 100 and work out what would they need to multiply it by to make it a square. In fact, let's separate these two out. How about a cube number? What's nice about this is you can really see, you can talk about, okay, cube numbers have to have multiples of 3 as their powers. they're two really, really, really nice extensions. So what we have here is a nice single, double lesson, probably single lesson, where you're practicing, or you're thinking about square numbers, cube numbers, you're thinking about... So when I talk to other teachers about this, we're going to do a like, what skills are we practicing here? And you can do this with kids at the end or beginning of the lesson. When I do it with teachers, like when I talk to teachers about this is what we'll be talking about. When we look at these two questions, what skills are we practicing here? The other, I don't really like this slide. I need to work out what the starter might be. I think the starter... I think it'll be this. I think when kids come in, this is the question that they're looking at. Oh, this is the question that they're looking at. And then they can just try it. Let's absolutely delete this comment. Do I know how to do that? You know what? Why don't we add a comment? Get students these questions, and then we will be going through them later in the lesson. Yeah, if you want kids to be, this also is a nice question to have, nice to have near the beginning, because it's getting them to look at simpler stuff. Okay, awesome. And there we go. That's kind of from question to extensions, how I might go about doing this with a class. I have no idea what ability that class might be, but with interested classes, just to look at how you can use some of the skills we've used in school to answer crazier questions. Like, look how crazy this question is without a calculator. So yeah, and some great extensions there. So let me know what you think, and thank you very much for watching. I'll put any relevant links in the video below. So thank you so much for watching however much of this video you watched. If you want to access the PowerPoint or want more information about it, I've written like a small blog post about it, which is going to be below in the things. Just trying something different, talking through the thought process. Also, I wanted to make that lesson, so it's fun to like talk about my process, and fun to talk about my process. So yeah, thank you very much for watching. Make sure to subscribe for more, and see you in the next one.